Well, it's a pleasure to be here. Thanks for the opportunity to speak. I want to talk about essentially really my journey towards understanding about reactive programming. So I started programming in the imperative style a long time ago, and then picked up functional programming along the way, and then separately came to know about reactive programming and got excited about it. And these two kind of were separate in my mind. And it was almost like an aha moment when I realized that these are actually not really disconnected. And in fact, they are pretty closely related to each other. And that's what I'm going to talk about here today. The talk is really not entirely about reactive programming, but more so how the functional programming concepts actually lead into or bleed into, depending on how you want to say it, into the reactiveness, and also talk a little bit about why we may want to consider something reactive. When do we want to be programming with maybe Java 8 streams? When do we want to maybe consider using reactive observables? So that's really my focus of my talk. Best time to ask questions or make comments is when you have it. So please don't hesitate. Anytime is a good time for questions, comments, draw my attention, and I'll be delighted to hear from you. So let's talk about functional programming to begin with. A lot of mainstream languages have been using pretty much the imperative style of programming for a very long time. And even when we programmed with object-oriented languages, we pretty much used imperative style of programming. So in a way, if you really think about it, what the world has been doing for maybe about 20 to 30 years is we've been mixing pretty much imperative plus the object-oriented. And it's kind of interesting how these two have played together for so long. We do create objects, we create classes, we encapsulate data in it. But when it comes to really writing code, it's really imperative style with object-oriented where we are mixing these together. And a lot of times people talk about object-oriented versus functional programming, and I don't see it that way at all. And the way I see it right now is functional plus object-oriented, and that is essentially what languages like Java make possible. Now in languages like Java and Scala and many other languages, we could use functional programming, but we could mix it with object-oriented programming. So in a way, I see that the direct real competition, if you want to call it as competition at all, is really between imperative and functional, not really functional and object-oriented. You could use functional without objects, obviously, but I don't think we should really worry about mixing with objects, because objects do play a role and we can put it to a really healthy use, provided we know how to really use objects. That is, we can definitely benefit from that. So from that point of view, what are we really gaining from this approach? Well, one of the disadvantages of imperative style of programming is that it is inherently more complex. I call this as accidental complexity. The complexity just really makes it hard for us to conceptualize and build applications in general. Let's take a look at one example here just to kind of entertain this thought. Suppose I started with a list of numbers, let's say, and what I want to do is to, let's say, find the double of the even numbers in this collection. So what would I do? I'll start with result is equal to 0. I want to output the result when I am done with this. But then what do? You say for, and then int I equal to 0, and then I less than numbers dot, and we have to think. Is it length? Is it size? Is it count? There doesn't seem to be any consistency. If it's an array, we would use a length. If it's an array list, we use a size. It depends on the language. It could be a count. And we have to make the decision as to what to use in here. And then, of course, right as we go through it, we have to ask the question, is it less than or equal to? These are very minor details we trouble ourselves with, and for every single one of these decisions you make, it is really slowing you down from getting your work actually done. And then what do we have to do after this? Of course, in this case, we could say, if the numbers dot get, again you make a decision, is it square bracket or is it get to get the data? And then you say if that is going to be an even number, well then of course we could say result plus equal to, and then we could say the numbers dot get I, and then times 2 to make the operation work. But of course, you already know this is a little too complex. It's very familiar but complex. We can minimize the effort in here by simply saying, given an element E from numbers, what a relief already. We could simply use the number E, and then of course here we could use the number E also. But nevertheless, what we do here when we write code like this is, we are still having to manage the loops. We do breaks, we do continues, we completely take control of the looping, and rather than getting our work done, our focus is on how to manage the loops, and that becomes quite a bit of effort. On the other hand, we could do this in imperative and functional style of programming. So what we could, functional and declarative style of programming. So what we could do here is we could say, for example, in this case, numbers dot stream. Well, it turns out stream is an internal iterator. And then we could say dot filter, and given an element, we could say element mod 2 is equal to 0. And then we could do a map to double in this case. This is purely because of Java conventions. And then of course we could say given an element times 2, and then we could perform a sum operation on it to get the result of this particular operation. Well, both of these code, in this case, of course, if I wanted to map to int, we could just do it as int as well. And both of these, of course, produce the same result. But what is the difference? Well, the very first difference is you had to do all the work in controlling the loop up here. Now, if you look at the code like this imperative style code, how does this code feel like? It feels like you're talking to a toddler. The first day you talk to a toddler, maybe it was very exciting. You talk to this little kid and it's so much fun to be talking to little children, right? But then the second day you talk to the toddler, you realize something very grim. You have to say the same damn thing again. And you have to say, walk slowly, look where you're going, step forward, hold what you're holding with both hands, don't step on the cat. And then the third day you say the same thing, and then you realize this is going to continue for the next 18 years. That's called parenting, isn't it? And that's how it feels when you write code like this in imperative style. You have to work extra hard at every single level of the detail and put your effort towards it. Well, this one, how does this feel like? It feels like you're talking to a responsible adult. You simply say what you want. You don't have to get into the details about how to really do it. It becomes a lot easier to express your intentions. It becomes a lot clearer. The second thing you notice here is we're dealing with mutability over and over and over. We are creating this result initially, but we are modifying that value over and over. Well, in this code, we don't have any explicit mutability in this code. And that removes, when you remove mutability in your code, it removes a lot of things you have to continuously reason and make true, make sure that it's correct. That removes a lot of burden from our shoulders as well when we are trying to get our work done. So that becomes a lot easier. But that brings up the question, what about, imperative versus declarative versus functional? What are we really talking about? Well, first of all, in the imperative style, one of the things we do is in the imperative, we say tell what, but also take trouble to tell how. And that is really the essence of imperative style of programming. You tell what to do, but you also take the trouble to tell how to do it. And that becomes your responsibility every step of the way. On the other hand, when it comes to declarative style, what you do is you tell what, not how. You can focus on telling what to do, but you don't have to focus on telling how to do it. So here is a way to think about imperative style of programming. I travel a lot. I have to go around, and when I travel, I want to be traveling, but that is the what is, I want to say where to go. And there are different people, and different people have different likings and different tastes. But for me, I just don't care about cars. So when I go to, if I have to rent a car, when I go to rental car, they'll ask me what kind of car you want. I'll say I would like to have one with wheels, please. And that's how much I really care about cars. I just don't really bother about them. And one thing you will never ever do is you will never catch me drive a stick shift, because I have no patience for it. It is way too much effort, way too much thing to think about. And so the worst probably I would do is maybe drive an auto transmission. But honestly, I don't really care for that. I am more of a Uber kind of a guy. So I get to the airport and I just call Uber and say, take me to the place where I want to take. and I sit in the back seat and I do coding, which is what I like doing. And trust me, the city streets are much safer when I do coding than when I do driving. So the point really is, that is kind of like the declarative style of programming. I say where to take me and leave the job to somebody else to do it, so I can focus on what I really care about, which is getting to the destination and doing my work, and I can focus on my core competency, which definitely is not in driving. So the point really is, when it comes to declarative style of programming, we want to focus on the what and not be dragged down into how. So we tell libraries of functions. So in this case, you can see we have several functions we could actually use. The other thing to consider is, in the case of imperative style of programming, here's a challenge I will pose for you. When you get to work tomorrow morning, do this, and it'll be really shocking when you do this. Go to your source code and do a grep and find out how many uses of for you have in your code. It's going to be scary, isn't it? Because every corner we turn, we use for loops, and that is like a hammer. So it's like you hear a knock on the door, and you open the door, and there's a guy with a hammer. You say, who are you? He says, I'm here to fix your kitchen. And you say, well, where are your tools? And he says, I don't need any sticking tools. I got this hammer. And you're probably going to let the guy in and step out and call the cops, because it's probably not safe to be in a home with a guy with a hammer, right? Well, that's what we've been doing. We've been using this for hammer every corner we turn. We've been using the for loops, occasionally a while loop, but mostly a for loop. Well, what are we doing in here though? Well, notice we're not using a for loop, but we're using a very specialized tools right here to, in the case of a for loop, you would use a break or you would use a continue. We don't have breaks and continue moving in the functional style, but these little tools come in really handy. So we have a little filter tool, a little map tool, a little reduce tool, and so on. So this is like a guy who walks up to the door and rings the doorbell. You look at this guy and he has a little bag, a tool bag, and he says here he's there to fix your kitchen, and you let him in, and you see that he's got little tools. He's got a little wrench, a little chisel, a little screwdriver, maybe a little hammer too, and that's exactly the point. Is there's the little tools, and you get to decide when to use which tool, and you put them to use. That's what you're gaining right here. But what in the world is then declarative versus functional programming? So one of the very first things I want to emphasize here is, the real charm, the real benefit we get out of functional programming truly comes, not entirely, but for quite a significant part, comes from the declarative style, where we can tell what to do and not focus on how to do it. So that is an example of the sum method that you see here. We said sum, but we're not telling how to perform the sum. That's left to this method for it to decide. And that's right there. This line here is declarative. Squarely, we can say that it is. On the other hand, what in the world then is functional if that is declarative? Well, I'm going to say functional is really declarative, first of all, plus you are using a higher order functions. So that is the combination to really go from declarative to functional style. So we are building on the declarative nature, but in addition, we are bringing in the higher order functions. So in this case, this is functional, and the reason why this is functional is because it is declarative. You said filter, you didn't say how to filter, but it's higher order because, so what in the world then is a higher order function? Well, let's step back for a minute. What are we used to? We are used to passing objects to functions or methods. Well, we are also used to creating objects within functions or methods, of course. And then finally, we are used to returning objects from functions or methods. Well, what we can do now is we can now pass. Well, what can we pass in this case? Well, we can pass functions to functions and methods. That's what makes it a higher order function. We could also create potentially functions within functions and methods. And finally, we could even return functions from functions and methods as well. So not just pass around data or objects, we could pass functions to functions. And that's exactly what we are doing here. So we have filter, but we are passing to it this lambda expression or the anonymous function to the filter function. And that's what makes this functional, because it's declarative but it also is higher order, and that makes it really functional. And that's exactly true about this one here as well. It becomes functional. So one of the key things about this is we go from imperative to declarative, but then we go from declarative to functional because we are not only able to do object decomposition, but we can do function decomposition as well pretty effectively when we start writing code. So that ability comes from having the higher order functions, and that works really well. But one of the things we constantly hear when it comes to functional programming is we are told continuously about honoring immutability. And this is one of the frustrating things when we are beginning to adopt functional programming is in languages like Java, we are so used to doing mutability. And then the functional programming gurus tell us, you will not mutate anything. And that sounds so odd. And you look at this and say, really? How do I write a program where nothing gets mutated? Well, actually, I'll show you a program where nothing ever gets mutated. And it's very, very beautiful. It's easy to write it in Java. And it's not that difficult at all. So there you go, a program that does not mutate anything at all. Well, but it doesn't do anything useful too. It's a little side fact. But how do we realistically create a program where nothing ever gets mutated? Well, one of the things to keep in mind in this case is the goal is not to say nothing gets mutated ever. The goal is to say that we don't continue to mutate stuff in our code. And the reason is when you deal with mutability, it causes really enormous amount of pain for making certain things happen. So why does functional programming emphasize that we should not mutate anything? And if we understand that, then it becomes a lot easier to A, appreciate the reason for it, and second, it also helps us to program towards that kind of immutability. Well, oftentimes you will hear people say, and I've said this several times myself also, is that if you're dealing with mutability, it's incredibly hard to program concurrency. So when multiple threads start running, it's really hard to make that code concurrent and correct when you start dealing with mutability. But that's only half the story. Well, concurrency is definitely one reason, but you may argue, gosh, if I'm not really doing parallel programming, if I don't care about concurrency, then should I really worry about it? Well, people will tell you, yes, you should, because if you decide to make it concurrent one day, you're going to be in trouble. Maybe that doesn't still convince us. What if I don't want to ever make this concurrent? Then is it okay to really, mutate stuff? Let's talk about that a little bit and see why this would be such a big concern and how we would go about dealing with it. Let's take a real quick example here. I've got a little code here which is going to create a people objects. So have a create a people, and you can see in this case we got Sarah, Bob, Paula, a bunch of names I have here. But maybe what I want to do is to, let's say, find the first female who is older than, let's say, 25. So how do I write that code in the functional style of programming? Well, we could first of all start with create a people. So that gives me all the people objects from this collection. And then I could say dot, and we could get a stream out of it. Then we could do a filter, and we could say given a person, person dot get gender, and then we could say gender dot female, and then we could say dot, and then we want person over 25 years of old. So we'll say person, and then person dot get age, and then we could say greater than 25, and then what do we want to do? We could do a map, and all that I want is the name of the person, so get name, let's say, and then finally we'll say find first, and we'll get the person's name. And in this case we'll say dot or else, we will basically say maybe no, not found. So this could be a result we are getting, and let's go ahead and print this out to just see what the output looks like. So this becomes the functional style to get this particular data and print it. Well, in this particular given collection, if I run this little code, person.getAge, obviously in this case, let's see where the error comes from. Get name, this is a method reference, there we go. So if you notice in this case, it tells us the value. I'm going to remove this little print statement I put in there. We'll come back to that later. So in this case, we can see that I'm going to get the result here of Paula. So that finds that the first person who is older than 25 and is a female is Paula, and we got the name right here. So that reads really nicely in the functional style, so that definitely is good. But one of the key things to keep in mind when it comes to functional style of programming is these lambda expressions. These are anonymous functions, and there's a rule that functional programming really expects. And the rule is that these functions, well, basically these are the lambda expressions, right, which are anonymous functions, must be pure. Now, what in the world does it mean that it has to be pure? Well, purity simply means they don't have side effects. So what does that really mean, they don't have side effects? Well, what that means is, given the same input, they give the same output over and over and over. So it doesn't matter how many times you call them, as long as the input is exactly the same, the output is going to be exactly the same. But a lot of times people forget one important requirement about purity of functions. So what is a pure function? Or I'm going to call it as rules of purity. Let's call it that way. Now, the first rule of purity, I can say that everyone in this room probably agrees to it very quickly. And that is, a pure function does not mutate or change anything, right? And I think we all can quickly agree to that, right? If you are having a pure function, you're not messing with any state anywhere. You're not changing some variables, definitely not variables in a shared scope. You're not going to change it. But this rule number one is necessary but not sufficient. You cannot claim a function to be pure just on the basis of this rule. Hey, I'm not changing anything, so I'm pure. No, time out, that's not true. That is a necessary condition but not a sufficient condition. That's not going to be enough. So what is then required? The rule number two is a pure function does not depend on anything that may possibly change. This is a much stronger requirement. So a pure function does not depend on anything that may possibly change. That is a very stringent rule, isn't it? Now the question is, why shouldn't a function depend on something that may possibly change? Why shouldn't it depend on it? This is where the concern of the impurity comes in, immutability comes in. Why should we really care about it? What's the point of doing all of these? What is the reason for aiming for that? Well, the reason is, let's go back to this little example and play with it a little bit. And in this case, I'm going to take this code right here. And let's go ahead and create a stream of person. And in this case, we'll call it as stream equals. And we will save the stream all the way up to here. So in this case, we have saved the stream, the filter and the map, and we have saved it down to the stream right here. And then what are we going to do here? I'm going to say right here a stream dot, and in this case we'll output it, and then here right here we'll say a stream dot find first. So once I find the first one, we'll say dot or else, and let's go ahead and say not found. And I'm going to go ahead and print it. So I made only a small change to the code to go through and bring it. Well, in this case, since we are getting a name, this becomes a string rather than a person, and the code still worked and produced the result. But notice this guy right here. Well, the person class doesn't have any setters. The person class is pretty much immutable. I cannot change the person in any way. And getAge is a function that returns the age value, and 25 is a constant literal. So looking at this function, it follows rule number one, which is it doesn't modify anything. Well, the good news is it also follows rule number two. It is not depending on anything that could potentially get modified also. So we could celebrate the purity of this function. But what if I change this code a little bit and say int max age is equal to 25. And then I come down here and change this to max age. Now the question is this function still a pure function? Well, a bit of a good news. It depends on the language you are programming with. Java is trying to protect you to a certain degree. So Java says, you know what, this variable max age is being used within the lambda. It's important for this lambda to be pure. So Java makes a very important decision. Java treats max age as final. It says this is as if you put the word final. So if I had put the word final right here, you would obviously not be able to change max age anymore. So if I try to come here and say max age is equal to, let's say 12, your compiler will give you an error on line number 28. And it will tell you, what are you trying to do on line 28? You're trying to change a final variable. You are not allowed to do it, right? So that makes really good sense, no doubt about it. However, in the case of Java, you don't have to put final right here. If you don't put final, and if that variable is being used within the lambda, it's not a problem, because what Java assumes is when you declare a particular variable, it assumes it is effectively final. So effectively final means you treat it like you put the word final in there. It's just that you didn't put the word final. This is purely for programming ease. Java just gently tells you, you and I have been going out for 20 years. We can trust each other just a little bit. We don't need these formalities of final in the code. But then when you come here, and if you don't have the word final up there, but if you try to change it right here, then Java says, I thought we had an understanding between us, right? And it tells you that you're violating this accepted contract, unwritten contract that you have with Java. But where is the error going to come from? Notice the error now comes from within the lambda. And the error says local variable referenced from a lambda expression must be final or effectively final. So, but why does Java give you this error? The reason Java gives you this error is this function is no longer pure. It doesn't modify any variable, but it depends on a variable that possibly could be modified. And that makes this function impure. And playing with impurity and functional style is a really bad idea. And that's why Java is trying to protect us and say, don't do this. But you know how some programmers are very dangerous programmers? They will roll up their sleeves and say, let me show you how to do this. Stay away from them. Because what they will tell you is, they will come in here very sheepily, and they will go ahead and put a square bracket, and then they would come here and say new int square bracket, and then they would put it like this, and then they would come in here and they will put a square bracket like this. When you write code like this, Java will no longer complain. But if you look closely at the compiler, it'll shake its head and say, who are your parents? How do they bring up to you, you to be this way, right? And it's very disappointed. In fact, if you write code like this, if you come to work about 2 in the morning, the compilers get together and they compare code and they laugh at us. Because this is not supposed to be written this way. They try to protect us to a certain degree, and then they just kind of give up. But what is the consequence of this? Well, the consequence, unfortunately, of this is, notice we said max age is 25 right here, and we come down to this code now, and then we say square bracket 0 equals 12 right there, after we had written this piece of code. Now when we come back and run this code, the result is Sarah and not Paula anymore, even though we had set the value of max age and then used it on line 25 and then only changed it. Well, keep in mind, this code has nothing to do with parallel. It's definitely a sequential code. So what are we really getting to? Let's step back and talk about probably one of the most interesting features, in my opinion, about functional programming. When I talk about functional programming these days, honestly, I don't get excited about immutability, because that's not what we really are after. Telling programmers they should program immutability is like trying to tell children that they should eat vegetables. No doubt, and nobody likes doing it. So what is the real incentive for doing any of these? That's what we really want to focus on. Well, the very first charming feature of functional programming is function composition. Notice how beautifully we are able to take this result of this function, pass it to the stream, take the result of the stream and compose it into filter, take the result of the filter and compose it in another filter, and then take them and do a mapping. That becomes the function composition. So one of the key strengths of functional programming is composing all these functions together. If you're interested, Google for this beautiful blog that Martin Fowler wrote. It is called a collection, a pipeline pattern. And this is a blog post by Martin Fowler, and he talks about how we take the collections and run it through this pipeline of operations. And that is one of the biggest benefits we get out of this is this function composition. But beyond this function composition, one of the real big benefits we get out of this is that streams fundamentally, or in other words, this collection pipeline fundamentally is lazy. And that lazy evaluation is really the most charming feature of functional programming. Now, what is happening in here? Well, I'll tell you one of the things about streams is, streams and my children share one common feature. They both are lazy. I have teenagers. If you have teenagers, you know what I'm talking about. If you remember the days you were a teenager, you definitely then know what I'm talking about. Teenagers are absolutely lazy. And I've seen this at my home. My wonderful wife will tell my son, hey, turn off the TV. It's like no words were spoken. Nothing happened. The TV is still on. Then she says, hey, throw the trash out. No muscles were moved. Then she says, do your homework. No pencils were picked. Then she says, I'm calling daddy, and everything works at that point. So this is basically how streams work. And they could have called this as call daddy, in fact, for all practical purposes, or call mommy, depends on the house. Some houses, moms are strict, other houses, dads are strict. In my house, I'm supposed to be the strict one. So, nothing gets done, but the minute they say, I'm calling daddy, daddy could be thousands of miles away, but calling daddy really works. And the whole point really in this case is, you have the stream, but you are building up this pipeline, but the pipeline was never evaluated. So in that sense, I want to distinguish between two different things in here. Let's think about the word list versus the word stream for a minute. So these two are very distinct. Think of the word bucket and the word pipe. And what is the difference between a bucket and a pipe? The bucket is where you store the liquid. So I could take a bucket and I could fill water in the bucket and I could carry the bucket around. And you can put your hand into the bucket and there's water in it. And a list or a set is a collection like a bucket is. But on the other hand, a pipeline is not where you store liquid. A pipeline is where you pass liquid through. So I could have a tap. There may not be any liquid in the tap at all. I might open the tap and the liquid may flow through at that point. Sometimes, if you had a cleaning, there's air that's filled up and then it runs through. But the point is, a pipe is not for storing liquid. A pipe is to pass liquid through, but a bucket is where you store the liquid. And that is exactly what we're doing here. While a list or a set is a bucket or a container, a stream often is just a pipeline. But it's a pipeline that's evaluated lazily, and that is one of the most charming features of functional programming. As it turns out, if we do not honor the purity of functions, then what happens? The laziness totally breaks. When you deal with a purely functional programming language like Haskell, you cannot modify variables. These languages don't allow you to modify variables within functions. These languages enforce purity of functions. Languages like Java don't enforce it. Java especially is a little notch better than some of the other languages because it gives it that little thin layer of protection. If it's a local variable, it says, don't mess with this. But if it's not a local variable, if the variable is on the heap, if the variable is an object member, then it throws its hands up and says, good luck with it, hope you know what you're doing, right? So it's our responsibility to make sure we don't mutate stuff, because the minute you bring in, what happens in this case? So so in the presence of mutability, efficiency and laziness go away. This is one of the biggest reasons why we have to be very, very, very careful. So in the presence of mutability, efficiency and laziness totally go away. It's not just about parallelism, it's about efficiency that we have to be very careful about. That becomes extremely important. So I'm going to wrap up that by saying that efficiency is attained not by doing things faster, but by avoiding things that shouldn't be done in the first place. So if you want to be really, really efficient, you can never be more efficient than not doing something. And that is one of the beautiful things about laziness. Imagine it's January 15th and the boss calls you in the office and says, I've got a good news for you. I've got a new project you're going to work on, and I need the report on April the 15th. So what do? On Jan 15th, you say, boss, this is great news, thanks. And then you come out of the office and get back to your desk and immediately start working on it, right? No. You will promptly start on it on April the 14th because you know you got to submit this report the next day. But in fact, you know something the boss doesn't know. You've already decided to quit on March 1st. Why in the world would you start working on this, right? And of course, in this case, you can escape that because the boss wanted something only on the April the 15th. There's nothing for you to produce before then, so you can keep postponing it. On the other hand, there are some really boring bosses. And the boss tells you the final report is due on April 15th, and you know what's coming, right? An interim report is due every Friday. So you better start working at least on that Thursday night because something is due on that Friday. In other words, if what you do becomes visible, you cannot be lazy. If what you do doesn't become visible until the very end, you can be absolutely lazy about it. And that is one of the biggest strengths of functional programming. But what is the benefit of being lazy? The benefit of being lazy is you can postpone doing work. And why should we postpone doing work? That means I can focus on what is imminent right now. I don't have to do this other work right now. That becomes really beneficial. And that way I can focus on what's really useful now and not do things that are not useful at the moment. Second, when I postpone it so much, it comes to a point where I realize I don't need this at all. Then I'm not wasting my time doing work I don't have to do. And third, at the time that I do have to do the work, I can do it minimally rather than doing so hard and doing all the work. Let's take a look at the laziness in this code just to see how this actually works to our favor. So let's get rid of all of these guys for a second. Let's even merge these two so that we can take a look at all these output together. So in this case, we have this map function where we are getting the a collection of all these names, and then we call the find first on it. So what I'm going to do here in this code, we'll just go ahead and output this result and take a look at it. But if you look at this now, well, you notice that we have a collection of people right here. And I have said that in this case, max age is 25. In fact, let's just go ahead and say 25 right here and be done with it. So in this case, we can see that we are asking for this object, which is Paula. But if you look at this code, we got Sarah's and Bob's and Bob and Paula, but then we have Paul, 2 Jacks and Jill. What about this Paul, Jack, and Jill? Well, if you look at this, this says I'm going to get the gender of everyone. Well, and then I'm going to get the age of everyone. Then I'm going to get the name of, well, age of every female. And then I'm going to get the name of everybody who's 25, older than 25. But discard everything and get the very first one. That sounds horribly inefficient, isn't it? And if functional programming was doing this, and make no mistake, a lot of languages which provide functional style of programming actually waste all those computations, and they are not efficient. Just because a language provides functional style doesn't mean they can provide lazy evaluation. This is one of the things I really got excited about Java is Java didn't give us lambdas and function composition and say good luck with it. Instead, what Java did was it cared about efficiency and gave it to us. So in this case, these functions, which are intermediate functions, are fused together and they are rolled up into one function that's going to get evaluated. So as a result, this code is no less efficient than the imperative style code you're going to write. And that is one of the benefits you get out of this. To prove the point, let's go to the person class. And in the person class, I'm going to put the getAge, I'm going to put the getAge called for name and print it. And generally, it's not a good idea to do this because when you want functions to be lazy, you don't want side effects. So this is an example of don't do as I do. This is just an example. Don't do this in real life. So what am I going to do in this case? When I come back and run this code this time, you will notice it called the getAge for Sarah, and it called it for, it didn't call for Bob, obviously, because Bob is not female, but it called for Paula. But what about Paul, Jack, and Jill? In fact, we can go back to this code just to prove it even further. Let's go to the getGender, because that's what we are calling right here. So let's go to the getGender function, and in the getGender function, let's go ahead and print out right here. We'll say getGender called for, and we can see what it is being called for, what names. And when I run this, you notice it never actually called it for Paul, Jack, or Jill, because the find first says, I got what I'm looking for, you don't have to do any more work. That is laziness. So laziness gives us efficiency, and that's why immutability becomes important. But to me, the most charming feature of this is laziness. Suppose somebody comes to you and says, do you get excited about object-oriented programming? Well, what is object-oriented programming, if you really think about it, right? In object-oriented programming, there are 4 pillars of object-oriented programming. We have abstraction, and then we have, of course, encapsulation. Then we have, of course, encapsulation. Then we have, of course, inheritance. And then what do we have finally is polymorphism. So yes, sure, we have four of these. Well, what about encapsulation? What about abstraction? Abstraction is not new at all to object-oriented programming. Humans have been doing abstraction for very long time. Plato was probably one of the first guys who documented abstraction. He said, if you draw a picture of an apple, it's different from the apple, it's a representation of the apple. We've been dealing with abstractions for a very long time. Any program you ever wrote has abstraction in it. So that's not the most charming feature of object-oriented programming. Sure, it is necessary, but not sufficient again. What about encapsulation? Well, that's very important too. But encapsulation is also not new to object-oriented programming. We've been doing encapsulation before. You could put a local variable in a function that's encapsulated already, isn't it? So we could do that too. What is inheritance? Inheritance is really how you inherit pain in object-oriented programming. That's what inheritance is for. In fact, a lot of object-oriented languages don't even require inheritance, so that's not a required feature for object-oriented programming. It's a bit of a misguidance. In fact, some of the languages like Java and C# and C++ made sure we cannot use polymorphism without inheritance, and so we walk around thinking that inheritance is actually important and necessary, but that's not true. Those are mostly language constraints. Well, what it leaves behind is polymorphism. Polymorphism is the most important feature of object-oriented programming because polymorphism gives us extensibility. And without extensibility, there's really no reason to be doing object-oriented programming. So polymorphism is to object-oriented programming, and in a way as a function composition and lazy evaluation is to functional programming. So the real charm of functional programming really is that function composition and lazy evaluation. That's what we really are after, and that's what gives us efficiency. So that was my realization about functional programming, and I got really excited about that. And then came along things about reactive programming. And like I mentioned in the beginning, I kind of started looking at these two somewhat disjoint from each other. I had played with functional programming on one hand, I started playing with reactive programming on the other hand, and I was honestly struggling to figure out where does this really fit in. In my mind, I struggle for clarity. I struggle for knowing how things relate to each other. And when I don't understand this, it becomes a pure frustration. In my career, I have probably gone through 3, if not 4 paradigm shifts. And every one of those paradigm shifts were horrible times. Because every morning you wake up with a cloud over your head, and things don't make any sense. Until a few months ago, programming was nice and happy and easy. And then somebody introduces me to this other paradigm, and that gets very exciting. You start digging in, and that causes more confusion than clarity. And then every morning you wake up, and before you could put your foot on the ground, you think about this and say, why is this not clear? And sometimes it's taken me a couple of weeks, sometimes months to really figure out. And then one morning you wake up and it's like all the fog has cleared. It's very clear in your mind, and you're like, gosh, why did I have so much trouble really understanding this? And every time I go through this kind of paradigm shift, it is very frustrating going through it. But when I come out of it, it seems to be a very wonderful journey, assuming that you do come out of this on the other end. And that is exactly how I felt when I started learning about functional programming. It was very frustrating, and what I was familiar with was making it really hard for me to adapt to the functional style of programming. When I started looking at reactive programming, a lot of literature on reactive programming do a lot of hand waving. They tell you all the wonderful things you can do, but I have to see code. I have to touch and feel and get things moving before I can say, yeah, this begins to make sense. So I was struggling with this quite a bit and trying to really write code to see how this is going to work. And so what is really reactive programming? And then we'll see how that really ties back to functional programming. Well, reactive programming is really not new at all. So why do we really have a new, different programming model? Well, I realized that we work in a field where right about every 10 years, we'll give a new name for what we already do and get really excited about it. So this time you hear things like microservices and reactive programming. So a lot of stuff we've been doing for a while, but the new name just gives us new energy and new excitement around these things. But these have been around for a very long time in terms of what they provide. Pleasure, thank you. Yeah. As a result, when you have these things, when you see what this actually means. So what in the world is reactive programming? Well, Eric Meyer, as part of his work in Microsoft Research, coined this term reactive programming. It's been around in Microsoft Word for a long time. And eventually, of course, the Java developers and the JavaScript developers, found this out. But you see, I work in, all of these technologies, and I have really good friends who work in Microsoft technology. And then, of course, friends in Java community and JavaScript community. But there's one thing very distinctive about these communities. You go to the Microsoft community and give them a solution, very, very wonderful developers. They will take the solution and immediately focus on creating value. You go to the Java community and show them a solution, they will get excited and go off to create 20,000 frameworks around it. And this is what really got this word out, because people really said, whoa, look at this reactive programming, and look at how many solutions you have on the Java side. It just blows up, and same thing on the JavaScript side, for example. People get really excited about it. Well, but is it really a new programming model? Well, it turns out it's really not. So a reactive application is the one that responds to stimuli. So as things happen, it's going to respond to those things. One of the best known reactive applications is maybe older than me, actually, which is kind of hard to believe, but it's true. And that example is Microsoft Excel. Well, Microsoft Excel is so ubiquitous, we all have used it, but think about Excel for a minute. You could have literally thousands and thousands of cells, but you may modify one cell over here, and before you could blink your eyes, all the other cells that depend on it update instantaneously. Not only that, all the cells that in turn depend on those cells update immediately, and more and recursively. Before you could blink your eyes, all these change to the change you make. So you make this one change here, and you see all this reflect through the entire system very quickly. That's an example of a reactive application. A reactive application is an application where the application responds to stimuli instantaneously. I discovered reactive application in a somewhat of a different way. I travel around the world constantly, which means I'm usually in some remote part of the world, stuck in some hotel. And because I travel so much, I live what I call as a virtual nomadic life. And most of my communication with my family is through electronic documents, which means I share Google Docs with my wife and my children. And this is, nothing exciting about it, but I discovered this one morning and I was blown away by this little revelation I had. So one fine morning, I was in some remote part of the world. I wake up in the morning and I log on to Google Doc. And at that time, I realized my wife was using the Google Doc exactly at the same time. And Google Doc actually showed the cursor exactly where she was editing. And I was able to put my cursor exactly where her cursor was, even though I was thousands of miles away, and I started editing exactly where she was editing. And with this, I found out you could be thousands of miles away and still annoy your spouse. And this is just unbelievably a good feature for me, because then she would say, "Get off my document now." I'm like, "Yes, madam." So the beauty is you could be thousands of miles away and figure out a way to annoy your spouse. That's reactive programming to me, right? So the point really is you could be collaborating on a document. You could have people around the world, but they could lively collaborate. They could collaborate live on editing a piece of document. That is a reactive application right there, for example. Now, why are we really interested in these kinds of reactive systems? Well, one of the reasons is we are not living in the world we used to live a few decades ago. I'm almost nostalgic when I say this. There was time when I would wake up in the morning, and as the coffee pot was brewing coffee, I would turn on my modem and it would connect, and I could hear that whoosh and then disconnect and reconnect, and then I can call my friends and ask them what baud rate they're getting that morning. Those days are long gone. We carry multiple devices with us today. I don't even know how many devices we carry with us now. The biggest geek personally I know is my son. The other day I patted him and several devices fell off him. I don't even know how many he carries. I couldn't confiscate enough of them in time. And now we are talking about wearable devices. Forget about watches, smart watches. We are talking about earrings, nose rings, and tongue rings, all internet enabled, constantly transmitting data. We're not far from the days when your doctor may call you and say, "Hey, I noticed your heart rate is fluctuating quite a bit now. I'm sensing some signals. Why don't you sit down?" And you can tell your doctor, "Oh, don't worry about it. Just listening to Venkat. It really happens when I do that." But the point really is that they could be monitoring us remotely, and they could be administering help for us health-wise. We're not very far from those days. We could be walking around or moving around, and we may have applications running on our smart devices that could alert us to imminent threat nearby, maybe a really bad weather. I was in Oklahoma, and I was looking at the newspaper, and they were telling this year, and it was only halfway into the year, and they said this year we have had only 264 tornadoes. And I'm like, are you crazy being in a place like this, right? But can you imagine, you are in a tornado path. Wouldn't that be nice to be notified to say, "Hey, you are in the path of a tornado, get yourselves to safety"? That can be really helpful. These are not great ideas that could happen. These are already beginning to happen with applications right now. So that's an example of how applications can be very reactive to the conditions we are in right now and respond to it. We could be dealing with stock data. Maybe I'm interested in purchasing the stock price, but the price is not quite where I want it to be. So I could be waiting for this price to reach a certain value, and the minute it hits that value, I'm ready to perform a trade. That could be another application of reactive systems. But if you think about it, where have we been for the past about 20 years? I think most of us have lived in the world of CRUD. We create CRUD applications mostly, right? I have created most of my applications have been CRUD applications. You read data, you update data, occasionally you delete data, and you create data. So you're creating data, reading data, updating data, and deleting data, and you then ask the question, is everything a CRUD application? Sometimes you work with developers and the very first thing they do is they create a database before they do anything else. And that becomes the norm. And then you kind of wonder, are we just all focused on creating CRUD applications? Well, it turns out it doesn't have to be that way. There are a lot of applications where we are not interested in CRUD. Maybe we're an intermediary. All that we are interested in is noticing this data that comes through, and either we ignore it, or we take certain action, or we transform the data and send it along. So you could be this middle layer that is all it's interested in is to receive a data that comes through, do some processing or transformation with it potentially, and just send it off to the next one which can handle and go through. In other words, what we are talking about is, what if you are one of those pipes in the pipeline? And so what if your application, that your little micro application you're building is a pipe in the pipeline? And if you're a pipe in the pipeline, data arrives, you do a transformation and you push it, and that's all you care about. You don't have to worry about where in the pipe you fit in, because that could be a business of the overall application where that could be formulated. So we are going towards directions where we can build these little components, if you want to call them components, but they are actually function units that are receiving data, transforming data, and pushing it through. And we are beginning to really think about architecture and system design in this way. And in that case, what are we really dealing with? We're dealing with streams of data. Well, this leads to the concept of data flow. So what is a data flow? A data flow is where you have a function and you have an input coming into this function. Let's say this function requires an input X and it requires an input Y, and the function is going to produce an output of, let's say, Z. Well, in a typical von Neumann architecture, you have instruction sets. And when you have an instruction set, you cannot execute an instruction until the instruction before it actually gets executed. This is true even in parallel processing, isn't it? You can run chunks of code in parallel, but those stages that you create run in sequence within that, and they follow this scheme of instruction I executes, instruction I plus 1 executes, and that's the way we do things. Well, in a data flow, you have a function, but a function is ready to fire, as they say it, as soon as maybe the input values become available. Data flow gives you the true concurrency, because in a true data flow system, multiple functions become excited and active as long as the input for them are right. If you were programming in the 1980s, you couldn't have survived the 80s without hearing about data flow. This was the big deal, just like how we hear about things like microservices and reactive programming today. If you were a kid in the 80s, you heard terms like data flow every day you wake up. And if I come to you and say, I got some great news for you, you can do data flow computing today, you're going to say, Grandpa, sit down, we don't care about it. But if I tell you we could do Amazon Lambdas and serverless programming, you're going to say, oh my gosh, this is so exciting. We just rebrand the same stuff over and get excited about it, right? So what is Lambda really? Well, it's a data flow because there's no server affinity. A process can come to life, do the work, and die away. Well, a lot of these concepts appear really new to us, but they've been around for a very, very long time. We just rebrand them and get really excited about it. So the idea of data flow is definitely very vibrant. And so what if we can think about this as a stream of data, and we can think about data flow. And then we can then say we are interested in transforming this data along the way, and then we become this intermediary to take this data, perform some transformation, and push it down and send it off for other processing. Well, so in a reactive application, what are we really focused on? Well, just like how object-oriented programming says there are 4 things very important, reactive programming says there are 4 things that are very important. Now, keep in mind, these are not new at all. They've been around for a very long time. In a way, reactive programming is kind of like extreme programming. Extreme programming, what is cool about extreme programming is it didn't introduce anything new at all. And yet it was so popular. Why? Because it said, here are 12 things that people are already doing, and we should really do these 12 things. That's exactly what XP did, right? Extreme programming did. Well, exactly what reactive programming says. Reactive programming says, here are 4 things we've been doing already, but these 4 things are really important for us to focus. So what's the very first thing? The very first thing is elasticity. We're living in a very different world today. I spent my youth as a system administrator. So I used to go to work, and my job was to install those huge Dell machines and Sun Microsystem machines. These machines were bigger than me and heavier than me. And poor little me, I was about 100 pounds back then. And it was really hard for me to lift these and install them. And then I would spend the nights literally upgrading servers. And I would never ever wish that on anyone, even my enemies anymore, because those were really, really hard days. You have to physically do all this work. And now in today's world, a company seriously cannot survive by having humans maintain these infrastructures. I have a client that I was talking to, they're a multi-billion-dollar company, and I asked them a wrong question. I asked them, how many users do you typically have? And they said, oh, we got about 200 users typically, maybe 100 users. I was like, really? You guys are a multi-billion-dollar company and you only have 200, 100, 200 users? And they said, well, you said typically. On a given day in a month, people are doing some stupid admin stuff. Nobody cares. They're setting up accounts, setting up permissions. No big deal. But 2.5 days in a month, we got about 50 to 60 million people using our systems. Now, can you imagine when you are into a system where nobody cares about your system about 28 days in a month, and the other 2 days, 60 million people jump on it? How could you build infrastructure for that kind of scale? It makes no sense for us to be doing this, but the good news is we don't have to. This is what we have learned from elastic computing. Well, you can set up your systems so that they can come to life based on demand at runtime. They could be based on time, they could be based on the season, they could be based on the real runtime demand. And elasticity says, we will spin up servers when we need them, and when we don't need them, we'll just let them go, so we're not wasting resources. And I'm really a big fan of you pay for what you use. I have applications running on the cloud, and I will tell you I have no complaints at all. My monthly bills are not the same, and I'm okay with it. When I have more users and more users are paying for my services, I get charged a little bit more. And when I have fewer users, fewer people are using my services, I get charged a little less. And that's really great. I don't have to really sit there and do this. It's completely automated. Servers come to life when the demand goes up. Servers goes away when the demand is not there. That works remarkably well. So it says that we really have to focus on elasticity. The next thing it says is we should be focused on using message-driven systems. I'm going to say it is so 20th century to have a centralized database and distributed transactions. We live in a world of microservices. It doesn't make sense to have multiple microservices and a centralized database. That is such an oxymoron, because you could make a change to that one little schema and render all your microservices out. So you really want to engage in message passing across these different disparate parts of the systems. That becomes extremely important to be able to do. Again, we have had message-driven systems, tools that make this happen for a very long time. But reactive programming says we should definitely use these kinds of messages. Then comes along responsiveness. What is one of the most important things for an application? The application responsiveness is the most critical thing in today's world. A decade ago, what did companies do? Companies hired employees, and the real world users, customers, interacted with the employees. When employees use your systems, there's a name for them. They're called captive users. meaning nobody cares what they think. And companies would force applications on them, and it doesn't matter how much the application sucked. But today, we have real world users using these applications. We rarely go through employees. And it doesn't matter what the size of your company is, you're going to have more users than number of employees, hopefully. So the scale is enormous. And what happens when you have people using your system? We live in a world of instant gratification. You go to this application and the application is not responding, you're not going to say, I will wait. You're going to move along and do something else, and sometimes you even forget the applications and you don't even realize you have these applications over time because they've been really, really not so responsive. So speed, it's not the speed of getting the result, but the responsiveness is extremely important. Remember the day when you discovered infinite scroll. And you have been using this application, it's a little sluggish, a little slow, but that day you went and it's a snap, you got the result on the screen, and you're like, whoa, that was really fast. And then you scroll down and your brain is about processing the fact that there's nothing in the bottom, and before you could respond to that, it fills up with data, and then while you're looking at a part of the data, it's pulling in more and displaying it. And that's a very prudent solution for, showing you some result and going and getting more results along the way. That kind of responsiveness is very, very important. Well, imagine you go into a store on a Saturday morning and you see this clerk very busy in the store. What are you going to do? You're going to look around for a few minutes, look at the ceiling, look at the floor, and you're going to quietly walk away because there was no response at all. On the other hand, you walk into the store, and as soon as you walk in, the clerk who is busy with somebody makes an eye contact and says, I'll be with you shortly. What did you do? You probably waited for a good 15 minutes because you felt like you are important even though you know you're not. And the point really is, that's really the whole point about responsiveness. It hooks on the users when they see that the application is actually responding. And that becomes extremely important. The fourth thing that's very important here is resilience. What happens when applications fail? Let's make no mistake, applications will fail. That's the nature of application failure. But rather than pretending failure won't happen, what if we embrace failure? What if we deal with failure in a very graceful manner? I went on to book an international flight. I'll tell you how frustrating this one is. I went to book the flight, and I'm going through this page and entering all the data, selecting the flight I want, entering my credit card details, and the very last step, I click and the application fails. And I really, really had to book this ticket and move on. So what did I do? I take a deep breath and I try the second time, and guess what happened? It failed again exactly at the time. And call me desperate. I tried the third time. And the third time it said, success, your ticket is booked. And I was so happy. Except the next morning, I logged in and I found 3 reservations for me on exactly the same flight. I called the airline and said, I'm good, but I'm not that good. I don't think I'm going to clone myself to fly on your airplane. So you need to cancel it. And that's kind of silly, right? Yes, it failed, but it should really fail gracefully. It should at least tell me what really went wrong, in what stage it went wrong. I got no notifications whatever. I just got charged 3 times. I didn't know it at the time. And graceful failure is very, very important. But unfortunately, though, there are a couple of things we do really wrong. The first thing is we tend to really program the happy path too quickly. I've been teaching at the university for about 30 years. And I teach remotely these days, but I was in one of the conferences not too long ago, and I had a gentleman come up to me and said, hey, I don't think you remember me, but I took your object computing course, distributed object computing course back in 1998. I said, oh my gosh, I remember way back then teaching a distributed object computing course. Wow, that brings back memories. He said, I got a story to tell you. He said, oh, I love stories. Tell me the story. He said, well, I was in your course. I was taking this distributed object computing course, and we had a final project, and I was demoing the final project. And right in the middle of the demo, you walked up to my computer, disconnected the internet cable, went back and sat down and said, continue. My program crashed and I failed the course. I said, I'm really sorry, but why do you want to tell me the story of failure? I don't like to hear these tragedies. You should have told me a good story. He said, no, 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 there's a good ending. I said, how could there be a good ending after you failed my course? He said, you see, that made a big difference, he went on to say, because that taught me a really important lesson. And then he went on to say, today when I program in my office, I never let that mistake happen. You see, because in my office, in my cubicle, in front of me, I have a picture of evil Venkat, and I look at this picture every day when I code, he said. I don't think we want a picture of evil Venkat in front of us, but the point is we really have to program for resilience. That's extremely important. We cannot really take just the happy path and then get surprised when things go wrong. Well, so that is about reactive programming, but then where's the connection really? And that's what really was bothering me, because I kind of took these ideas and I learned about these, and then I said, well, this looks really interesting, but I kind of woke up every morning and said, I don't get it. And call me silly, maybe just me who didn't get this, but the point is, there was a little gap in my head I quite couldn't figure out. And then eventually it dawned on me, oh my gosh, it really is a good transition. Reactive programming starts where functional programming leaves us. Functional programming says we want to have function composition and we want to have lazy evaluation. Reactive programming starts exactly at that point. It starts from the composition and laziness. Reactive programming is all about this observable, which is kind of like our stream, but what it provides for us is this pipeline that we can program with. Well, as much as functional programming uses this function pipeline, the reactive programming has this function pipeline. And as much as functional programming is about lazy evaluation, reactive programming is about lazy evaluation. Let's take a look at an example to see what that really means. So I'm going to use the observable here. You could use any language, any tool for this, but I'm going to go ahead and say stock server.fetch, and I'm going to go ahead and say, let's call it as a get feed, and I'm going to provide a bunch of symbols to this. So I need a bunch of symbols. I'm going to say over here, let's say list of string, we'll call it as symbols right here, is equal to arrays, let's say arrays dot as list, and let's just come up with a few things, like say Google, and let's say MSFT, and let's say AMZN. So a bunch of little symbols that we can refer to. But once I give these symbols, what do I want to do with this? Well, I want to get a feed. So what is this get feed method going to do for us? Well, let's go ahead and implement the get feed, but this is going to return an observable of, let's say, stock info. Well, so what is this observable? An observable is much like our stream in Java 8. So an observable is like a stream. A stream can produce data. Now, a stream is different from a regular iterator. An iterator, you pull the data. In the case of a stream, you push the data. It's exactly the same with observable also. So at this point, let's draw the similarity between them and differences. So on one hand, I have a stream. On the other hand, I have observable. And what do we know so far? Streams push data. And what do observables do? They push data also. So big deal, why bother about it, right? We'll come back to that in a little bit. So given that, let's say, what are we going to do here? I'm going to go over here and say output, let's say starting to emit data. Well, actually, let's go ahead and say created observable. So created observable. And how am I going to create the observable? I'm going to say observable.create. And we use a static method constructor. And then we create, and in this case, I'm going to say emitter, and all I'm going to do is call emit, pass the symbols to it, and the emitter to it as well at this point. So a little function, that's great. Now what do I want to do? Well, now that I have that, I need to implement the emit method. So let's go ahead and implement the emit method, and what am I going to do in the emit method? I'm going to go ahead and say output starting to emit. So that's what I have so far, as you can see right here. But I'm going to go back to the other side, and I've got a feed, as you can see right here. And now that I have a feed on my hand, what I'm going to do is output I'll say got the observable, and I'm going to go ahead and say print that out. So I got the observable, and let's go ahead and run this code. But before I run it, well, what did I do so far? I got the observable on my hand. That's all I did. If you look at the observable itself, it started providing this emit, which is going to start emitting. However, when I go back and run this code, from the output, what you notice is it tells us created observable, and it says got the observable, so it printed this, but notice it quite did not do this part right here starting to emit. Now, why is that? Well, that is laziness right there. It says, I'm not going to really do any work. Hey, why not? Well, the observable says, I created an object observable here, and I gave it to you. Oh, what did you do? Well, I did nothing with it. Well, if you didn't do anything with it, it's only fair I don't do any work either, right? So it's lazy. It is not going to get cranked up. It's going to wait for you to really subscribe before it really starts to emit. In a way, both in streams and observable, it's the tail that wags the dog. So the tail is the one that wags the dog, saying, hey, I am connected, I am interested in the data, you can now start pushing. It's still a push, but you got to be receiving it before the push actually happens on the other side. That's laziness right there. So as a result, what you're seeing in here is this is going to start pushing when you subscribe to it. So what am I going to do? Feed.subscribe, and I'm going to say data, and in this case, I'm going to simply output the data that's going to be given to me. Now that I've subscribed to it, when I run this code, you can see starting to emit being printed right there, because you did subscribe. It says, okay, it's only fair, you are connected on the other side, I can start pushing the data now. I cannot just afford to be ignoring you. Laziness doesn't mean ignoring real work. Laziness is postponing work until you can no longer postpone it. So what am I going to do at this point? Well, at this point, it's a good time to really do some work. So in this case, what I'm going to do is, given these values, I could say symbols.stream, and for each of these values that you have provided, I could perform a map operation and say stock info, and I can do a fetch operation to fetch the data for those. And then for each one of them, I can go to the emitter and I can say on next and push the data or emit the data so that you can actually receive it. And the stock info is just an object that's going to go get the data for these stock symbols so we can actually see them come through. So when I run this little code now, you can see the Google stock price, the Microsoft stock price, and the Amazon stock price come through, and it was pushing the data for us on this site. So until this point, they appear to be doing almost the same. What's the big deal about it? Well, the big deal about observable is observables are data streams. Observables are emitting data just like streams do. But this is more so with Java 8 streams. There are some deficiencies with streams. Streams are powerful. Streams are lazy. I am definitely excited about streams. But just to be objective, streams have power, but streams have deficiencies too. And what is one of them? If I go back to this code right here, let's say, notice how we are calling these methods to perform some operations on them. But what if one of these methods were going to go wrong? What if it's going to fail? Well, unfortunately, in our industry, we haven't quite figured out how to deal with errors. Way back in time, some of you may remember this if you're old enough, we used to call methods, and the methods would return a positive value if it was successful and negative value if it was error. And then we realized, gosh, results could be negative too. Then what did we do? If everything went fine, return a 0. If things don't go very well, return an error code. Great idea, but where's my data? Oh, no worries. You send me a pointer to the function, we'll fill the pointer and send it back to you. One of the errors you had to deal with was you didn't send me the right pointer. That didn't go really well. Then we said, we got a way to handle all of this. We will use exceptions. This gave the power for programmers to put empty catch blocks and celebrate it. That didn't take us too far at all, right? In fact, the worst thing about exception is we call them exception. They should have called it normal. And we call it exception and we get really worried and excited when it happens. There is no reason to. And what happens when you deal with exception? Exceptions are pretty silly. They are like hitting somebody with a hammer when something goes wrong. You would never work with people like that, right? You make a little mistake, they hit you on the head. It's like, why'd you do that? Because that's wrong. I mean, that's what exceptions do. They disrupt your call stack entirely. And you're like, my gosh, why are you so aggressive? Why don't you just tell me something was wrong instead of blowing this call stack? So exceptions are very extreme. And it's even worse. What happens when exception happen in a multi-threaded situation? Can you imagine this? You got 1,000 threads running, about 150 of them blow up with an exception. How do you deal with it? If you want to think about how it'll feel in a physical world, imagine you run a daycare center, and imagine there are 50 kids in the room, and imagine 27 of them start crying exactly at the same time. That's how it feels. You don't know what to do, what to handle anymore, and that becomes extremely messy. With streams, unfortunately, how do streams deal with exception? Java 8 has a wonderful solution for handling exceptions in stream. And that can be defined in 2 words. It's called good luck. So essentially, there is no real good answer. Because when the streams blow up, your lambdas that you pass to the stream cannot throw a checked exception. Now, some people think, oh, that's okay. I can wrap this. This is dangerous, people, right? I can wrap this into a runtime exception and throw it as if that's going to cure all our problems. What it did was, it told the compiler, you shut up. I don't want to see this problem during compile time because it's fun to have these problems at runtime. That's what we are telling when we do this, right? So that doesn't really help us solve the problem. So if these functions were to blow up, how do we handle it? And the short answer is, there is no real easy way to handle it. But let's step back and see what we should really do. Well, remember, we are in a function pipeline. When you're in a function pipeline, your data flows through the pipeline and it gets transformed through it. So you take a data, and in this case, for example, I have a data coming through, but notice what I could do. I could potentially take this data right here, and I could perform a transformation in between. I could say map, and then I can say stock info, and new stock info right here. And then I could say, for example, the given stock info dot a ticker, and then the stock info that you gave me dot value times 0.9. I gave you a 10% discount right there. So we could perform transformations. Notice the stock price was at 925 a minute ago. The market is open, so it could change, but let's ignore that fact for a minute. But when I run this, you can see that it is applying that discount, and it's no longer 900 and whatever that was. But of course, if I go back and comment out the map line, you can see the actual price, the raw price come through, which is 925.8. Looks like it didn't change a whole lot. But in this case, of course, if I go back and run this, it's not 925. It's been transformed right there. So we could perform these kinds of transformations along the way. But in this age of transformation, you are in this pipeline. When you are in this pipeline, something becomes wrong right in the middle of the pipeline. What is the right thing to do? The right thing to do is to deal with this problem downstream. So you want to really keep moving forward and deal with it downstream. What if we treat the error like it is data? What if we don't treat error as, oh my gosh, this is exception, let's blow the stack and hit everybody around us? Instead, what if we say, dude, it's just a problem, we can deal with it, right? And so what if, when something goes wrong, if I don't slap you, but I treat you with enormous respect and say, dude, something went wrong, here you go, error message for you. And we can be respectful of each other. We can be civilized. I can give you the error, then throwing things at you. And that becomes a lot better way to program, isn't it? Well, that's exactly where the difference comes in. So in the case of observables, we have 3 channels. So what are the 3 channels? The 3 channels are data channel, then you have an error channel, and then finally you have a complete channel. So this is where observable begins to depart from Java 8 streams in that it is really baked with a really good way to deal with errors. So you have a data channel, an error channel, and a complete channel. So you go back to this code right here. Here is the data channel that we are dealing with. But I can also provide an error, and then I can output error like this plus data, plus error. I can print out the error, I can deal with it. And then I can also provide right here a complete channel to tell you output, and I can say done. So these are three distinctive things. So unlike a stream, an observer will clearly tell you, I am done, I don't have any more data for you. So in this example, if I go back to my observable, at the very end of this, I can say emitter.onComplete, and I can send you a complete signal. And once there's a data channel, data may go through data channel, but the minute a complete signal is sent, that data channel will close. You will never get any data from it once this happens. I'm not suggesting to write code like this, but just to prove this, emitter.onNext, and I'm going to say new stock info blah comma 0.0. You will never see that signal because we have completed and closed the door. So when I go back and run this now, you will notice that it has the price for Google, has the price for Microsoft and Amazon. You see that done, and it closed the data channel at that point. You're not getting any more data. But on the same token, notice that in this case, your emit method is running within a container, so to use the word. It's running in the container of the observable. So as a result, if I now go to stock info, and in a random time, I'm just going to blow up. I'm going to blow up with a very intellectual message which says, oops, ran into trouble, just like systems blow up right now, right? So I'm going to blow up right here in the bottom. But notice now, this guy doesn't know this. It doesn't know any of that. But when I go back and run this code though, at that random time, what is it going to do? Well, when it blows up at that point, it is going to take that exception, but wrap it as an error, and very civilized way, it gave us the error right there. It says error colon. Well, that came from here, as you know, and that's what it gave us the data right there. But of course, you could get some data before that happens as well. So in this case, you can see you got the Google prize, but then it failed after that with the error, but you are delivered the error through the error channel. Much like the complete channel, the data channel will send you the data, but the minute there is an error, the error signal is sent to the error channel, and the data channel closes up. So where I'm getting to with this is, while reactive programming is pretty exciting, this is not totally independent of other things we have been used to. In functional programming, we build function pipeline. In functional programming, we do lazy evaluation. We do function composition, and reactive programming does pretty much the same. As you can see, right there is your function pipeline in reactive programming. You can also see that this is a lazy evaluation. We saw that earlier. The things you put in here don't do any work until you subscribe. The laziness is part of it as well. So reactive programming totally embraces functional programming. So all your knowledge, all your investments, all the things you already do in functional programming carries over pretty straightforward. For example, I can say filter stock info.ticker is equal to, and I can say give me only Google stock price, nothing else, for example, and I can work with the operations like filter, if you will, very easily. Or what I could do is, for example, I could say, in this case, when you're giving me the values, give me the value, but only when the value is greater than, let's say, $100. So we could ask for filtering much like we do other things. And you can see Google and Amazon come through, and we can filter out. This can be sending periodic data for you. So all our functional knowledge and investments carry over. But at the same time, though, the observables say, we are going to take a very deliberate approach to how we deal with errors. And they follow the idea of circuit breakers. If an error were to happen, they close the data channel at that point, so it doesn't keep pounding you with data when something goes wrong, and instead gives you an opportunity to recover from it and deal with it. So that's been my journey in trying to take these two things that are, somewhat independent of each other, but realize that these are not really that far apart. All our learnings and investments in functional programming readily carry over to reactive programming, and it puts a little bit of a structure around what we do in terms of building applications. From an architecture point of view, there's no reason why we cannot start with functional programming and then grow into reactiveness when we need it. I'm a big fan of evolving architectures and postponing decisions until last responsible moment, kind of being lazy about it in a way. And so when we feel that we really need to embrace the reactiveness, we will be ready to do that. We don't have to make that decision up front. We can gradually move into it. And the beauty of that is these are not that far apart. These are really, one is an extension of the other. So I feel like reactive programming starts where functional programming leaves us, and it's a really nice transition moving forward. Hope that was useful. Thank you.